I was going to send you.
Oh, yeah, I said that. I have a voice recording.
I hope this picks up voice. Oh yeah,
Not every week, but yeah.
I'm gonna try to. I think it's a page paper due Monday.
I probably studied till like
4 or 7 of these are here.
Hey, did you notice I went straight?
You didn't try it, that you said? It just happened.
Well, we're still sitting.
It's the same way.
We're just.
That's a good or bad thing. Okay. A titration I grabbed from one of the groups. Weak acid, paper with base. Monoprotic, diprotic, triprotic, what is it? I would agree, you cannot tell. Could be monoprotic, might be diprotic, possibly even triprotic. Just by looking, you can't tell. Which is what you've all found the last couple of weeks with your weak unknown acid. They probably all looked monoprotic, but none of them were monoprotic. I believe I talked to Dr. Walbeck and she gave both of the Thursday group of diprotic for a try, right? But, so you can't necessarily tell just by looking. What can we say? What is true? pKa is around 8. I'm not going to necessarily agree with that statement.
You know where the equivalence point is, or one of them?
We know where an equivalence point is, absolutely. So we know that this is clearly an equivalence point. And most likely, which equivalence point is it? It's most likely the final. The first is monoprotic, the second is di, the third is tri. Because beyond that, we're up at almost pH 12. We're probably at about the pH of our base. We're probably not going to get much higher than that. Now, if that weak acid had another pKa that was somewhere around 12, then this would not be the final. But there aren't that many weak acids that have pKa's up around 12 or past that. So this is likely the final equivalence point. First is monoprotic, the second is di, etc. If it's monoprotic, then what do we know? Or what can we figure out? Half equivalence, let's work the half equivalence. pH equals pKa. If it's monoprotic. If it's diprotic, then what's here is a half at this point. Not particularly average. The first equivalence point would be there, and the half equivalence points would be here, halfway, halfway. If it's a triprotic, it's trichroic, then what? What do you say? It's trichroic means this is the third equivalence point. So if we divide this into thirds, roughly, here must be the third equivalence point, here must be the second equivalence point, and then to get the half equivalence, it's halfway between, so we have the first half, the second half, the third half. But just by looking at it, we can't tell. That's a bit of an aside, so we moved on to spectroscopy, but I wanted to make sure that we'd all done the lab before we talked about this, otherwise the lab gets really simple. You've already seen that. Okay, so we've been talking about spectroscopy, or last lecture we started talking about spectroscopy. And during spectroscopy, you are oftentimes, not always, but the majority of times, looking at absorbance. And for absorbance, negative log of the transmission, or it's log of 1 over the transmission. Where the transmission is the amount of light that goes through a sample over the amount of light that impinges on that sample, that hits that sample. What fraction of the light that shines on a sample and goes through the sample is called the transmission. And we can measure this with a relatively simple instrument. All spectroscopy instruments have a light source creating the light. They all have some kind of a wavelength selector. So we can pick which wavelength we want to look at. Remember we said molar absorptivities are essentially constant for a given molecule at a given wavelength, which is one of the reasons why we have to pick a wavelength to look at. And they always have a sample. The sample has some path like B, and then some kind of a way to detect how much light comes through. In this case, this is what's called a single beam. There's only one beam of light going through the system. Curve like that. And a single beam instrument, if you want to zero or blank the instrument, you have to manually put in a blank or zero, or whatever you want to call it, into the sample compartment, take a measurement and say, all right, this is my zero, this is my blank, and then replace it with your sample. So the advantage of single beam instruments is they're generally smaller, they're cheaper, they're more rugged. The disadvantage is you have to take out the cuvette and put in your blank, and then put in your sample. You could also look at double beam instruments. In a double beam instrument, there's still only one light source. There's still generally only one wavelength selector. So this is our selector. But the light that comes out of the source wavelength selector is then somehow split. There are various ways to do that. This one uses a rotating mirror, so if we're looking kind of at the side of this, if we look at this straight on, it would be a circle where half of it would be a mirror and half of it would be open. And as this mirror is on a motor and spinning, when the mirror side is in line, the light is reflected down through a reference cuvette where you can put in your blank material. When the motor is turned such that The open part is in line. The light goes through and goes through our sample. So now as this motor spins and this mirror, non-mirror device is spinning, light alternately goes to the reference and then the sample. And then the reference, then the sample, and the reference and the sample, and several times, usually several times per second, depending on how fast it's spinning. We then have a semi-transparent mirror, basically a little one-way glass, so that the light that comes from the reference gets sent to the detector, and the light that comes from the sample gets sent to the detector. So the detector is now alternatingly seeing blank or reference or zero sample, zero sample, zero sample. So in a double beam instrument, you don't have to first put in your blank the instrument, then put in your actual sample. It's constantly, you put in your blank and your sample, and it's constantly taking the blank and taking the sample alternately. This leads to better results, more precise results, more accurate results. But it's a larger instrument, it's a more expensive instrument, it's got moving parts. So there are more things that can go wrong with this instrument. You have probably all, I can't remember exactly what we got, I think we got them all before we started this first years. You probably all used a double beam instrument. The Shimatsus that I think are used in the first year lab, whether it's chubby lead or whether it's 121, 125, I don't know if this side, gray, they're double beam instruments. You open them up, there's actually two places to put a cuvette. Now you may have only used them as a single beam, you may have only used one cuvette. But they had, in that case, if you only used one cuvette, you were essentially blanking on air. Because the light was alternating, going back and forth between the front and back. So if you didn't put anything in the back reference cell, it was automatically referencing to air. So you've used double beams in that case. You will in lab today, tomorrow, Thursday, this week, be using a single beam instrument. I'll use it a couple of times over this time. All right, now that you've all done the calcium oxalate lab, and you've all experienced standard edition without having talked about it, now we're going to talk about it. So as you hopefully remember from that lab, in standard edition, we're going to take your unknown, you're going to take your unknown sample, and you're going to that unknown sample, add in some standard. That standard needs to be the same chemical species as what you're analyzing. So in the case of the calcium lab, you're trying to figure out how much calcium was in the liquid, and you doped in or you added in known amounts of calcium standard. So for standard addition, it is crucial that what you're adding is the same element or the same molecule or the same analyte as what you're trying to measure. So standard addition is used primarily, and managers heard this when I talked to them from the room, and hopefully they conveyed it back, but if not, standard addition is used primarily when you have a complex sample. Up to this point, up to the calcium lab, you have probably always, when you had to do a calibration, or Beer's law, plotting absorbance versus concentration, you've made standards of known concentration. You've made standards, you can see, of known concentration. You've made them in water, and you've then measured an unknown absorbance and used that to calculate the concentration of an unknown. And that's perfectly fine if the unknown is primarily in pure water. But if the unknown, the sample you're trying to measure is in something more complex. If it's in blood, blood's quite complex. There's hundreds of things in blood, and they change constantly. The components of your blood right now are going to be slightly different than the components of your blood after you have lunch. And they'll be even more different than they are after 4 hours of being in lab, is after when you're really hungry and want to get out of the lab. Or maybe it's a urine sample. Urine's quite complex. Here's even the can river water. You know, they say, well, it's water. There's lots of stuff in there, unfortunately. So anytime you have a complex background, a complex mixture, lots of stuff in there, you don't know if the other stuff, aside from what you're interested in, that other stuff is usually called a matrix. That's all the other stuff that's in your sample. You don't know if it reacts or if it absorbs. If it absorbs light, then you're going to get a signal that has a higher absorbance because not only is it your sample that's absorbing, so is something from the matrix, something that is in the sample that you don't care about, but it's absorbing. So if you make standards in pure water, run them, and get a nice calibration curve, get a nice R-squared value, everything looks great. You then run your unknown. If there are components of the unknown matrix that affect the absorbance reading, now we get an absorbance up here, which is going to lead you to calculate the concentration that is significantly off than what it really is of your particular analyte. So the way to fix this is to make up your calibration points in that exact same mixture of matrix components. That assumes that you can replicate that. It'd be virtually impossible, if not impossible, for us to replicate anyone's blood completely. Now you can get blood that's quite close, you can make blood samples, but it's not going to have the exact same amount of vitamin C or the exact same amount of aspirin, the exact same amount of whatever you took this morning, or the exact amount of tea that, or whether the component of tea that are being drank, or coffee, or whatever you're drinking, or this. So it's going to be different. You can't replicate it exactly. So that option is kind of off the door. So instead, standard addition is used. In standard addition, we're going to make sure that every one of our calibration points has the exact same amount of the unknown in it. Therefore, it has the exact same amount of matrix in it. Therefore, if anything in that matrix, anything in that background, is affecting the absorbance, it will affect all of the readings in the same way. Not just affecting our unknown measurement while not affecting our standard ones. So by mixing the actual unknown in each of these, we have the same amount of matrix in each of them. We have the same matrix effect. We have the same, whatever the effect is from whatever's in the background. Even if we don't know what's in the background and know how it's affecting things, we can say that it's affecting each of these data points in the same way. Because each of these data points have the same amount of matrix. So what that means is it's important to always add the same amount of unknown to each of those 5 data points. It also means that ultimately at the end, you want to have diluted each of the unknown samples by the same amount. So each of these needs to start with the same amount of unknown, the same amount of matrix, and at the end, we want the concentration of that matrix in all 5 to be the same. In other words, you have to dilute them all to the same level. What's different between them is how much standard we've added. So in your case, a couple weeks ago or a month ago, how much calcium. This one you added no calcium standard to, it just had whatever calcium was in the sample and the matrix. This one added some calcium, this one added some more calcium, some more calcium, some more calcium. And then they all had water added to them. to bring them all up to a constant volume. So this one had the most water added, a little bit less because it had some standard added, a little bit less water because it had more standard added, even less water because it had even more standard, etc. If that's the case, they all have the same amount of unknown, therefore the same amount of matrix, therefore the same matrix effect, and they've all been diluted to the same amount, then that effect of the matrix will be the same amongst all of them, and we're essentially subtracting it out. If we then extrapolate to, this is absorbance on the y-axis, this is concentration of standard added on the x. Not overall concentration, because we don't know the overall concentration. We might have an idea of what the unknown is, but we don't know what precisely is we're trying to figure out. So we plot on the x-axis the concentration of the amount of standard added. That we do presumably know accurately and precisely. So we extrapolate back to when the absorbance is 0. If the absorbance is 0, the concentration must be, not a trick question, 0, right? Here's law. A goes to 0, concentration must go to 0. So when absorbance is 0, concentration is 0. Or in other words, at this point, the concentration of whatever we're analyzing, calcium from a month ago, must be 0. That corresponds to a negative concentration of standard added. Well, a negative concentration is essentially saying how much concentration would you have to take out of this sample to make the absorbance 0. So if you have to take out so much, that must be what was there at the beginning. So we can extrapolate this back down, and the absorbance is 0. At that intercept, we'll get a negative concentration of standard added, and that negative value must be the concentration that was in each of these points from the unknown. And therefore, that must be the amount that was in the unknown to start with. Well, if we don't have all these points, we don't have 5 data points, which is the best way to do it, to graph several points so you can get a nice fit line. But if it's 4:55 and lands until 5 o'clock and you're really hungry and you want to get out of there quick, we can essentially do a 2-point measurement. Not going to be as good as the full calibration curve, 4, 5, 6 points, but it will be a quicker way to at least get a rough idea. So we can measure the absorbance of the unknown. We measure absorbance, that equals molar absorptivity times path length times the concentration of that species, X. We can then add a known amount of the analyte, or standard. So we're going to add some standard. And then remeasure. Well, the final then absorbance measurement will be the molar absorptivity times the path length times the total amount of that analyte we've added. The amount that we started with plus the standard that we've added. But what's happened to both of these concentrations compared to steps 1 and steps 2? They've been diluted. So we have to calculate what their new concentrations are in terms of what they started with. And then we can set up a ratio. The absorbance initial over the absorbance of the final mixture once the standard is added is equal to the concentration of the initial over the concentration of the final mixture. Essentially, molar reflectivity and path length being constant, and when we set up that ratio, they cancel out. So for example, if we have a 10 ml solution of ibuprofen, with all the concentration, and it's in a complex mixture stuff, we measure a standard absorbance of 0.5. We then add 5 mils of a 0.1 molar solution of known ibuprofen. And using the same system, the absorbance increases to 0.85. We should now be able to calculate the concentration of ibuprofen in that original sample. Now we can't just look at molar activity and path length of ibuprofen and say, well, the absorption is 0.5, and therefore the concentration is something. Because if it is a complex backbone, if it is a matrix, there might be other things that are either suppressing some of the absorbance, or that are absorbing and increasing and giving us part of that 0.5 reading. We don't know that this is an accurate reading that comes from just the ibuprofen. There could be other things in that matrix, in that mixture of stuff that's affecting the reading. So, we've added 5 mils of a 0.1 molar solution of ibuprofen, and it's now in a final volume of 15 mils. We started with 10 mils, we've added 5 mils. So we added 5 mils to the standard. The standard had a concentration of 0.1 molar. But it's now, once we've added it to our unknown initially, it's in a final volume of 15 mils. Or in other words, the concentration of ibuprofen that we've actually added at this point, including the dilution effect, is 0.033 molar. After we've added the standard, the concentration of the unknown ibuprofen has also been diluted. We started with 10 mils of it. It had some concentration. We don't know what that is yet. That's what we're going to figure out. It's now in a final volume of 15 mils because we added 5 mils of the standards to it. Or in other words, the initial ibuprofen. So if we could tell them apart, the ibuprofen that was in the unknown originally is now 0.667 times what it started. Because it's been diluted a little bit. Only 2/3 as concentrated as it started off. So if we can tell the two sources of ibuprofen apart, the original ibuprofen in the unknown is only 2/3 its concentration, and we've added 0.033 molar of new, fresh ibuprofen. We can't tell them apart, they're mixed together. But we can now set up our ratio. The absorbance initially over the absorbance once we've added our standard is equal to the concentration initially over the final concentration, which is 0.667 times the initial concentration plus 0.033 molar. This is what we started with. This is after we've added the standard We've diluted what we started with to 2/3, and we've added 0.033 molar. One equation, one unknown. We should be able to solve this. If we solve, we get x divided 0.032 molar. We're okay with that? Because we know what's coming. Chance for you to do it. So in this case, we start with a 25 ml solution of normal cresol purple indicator with some concentration of some complex mixture, matrix. And it has an absorption of 0.253. We then add 10 mils of a 0.15 molar standard solution, and the absorbance goes up to one of these values. I know which company you are. So the question is then, what is the concentration of the indicator in the original unknown solution?
Absorbance like 0.235 over 0.3 equals xi over 0.714x plus 0.0429.
Yeah, I'll carry that. I got the same thing.
Okay. Let me see. You got 6.01 times 10 negative
6.4.
round here.
A lot of numbers, visual. Total, a lot of numbers.
Yeah.
And it is. Okay, so now, whether you only have a couple of data points and you solve mathematically, whether you have several data points, which is a better way to go, and you do it graphically, you should be able to use standard addition and calculate concentrations in the original unknown. So standard addition is routinely used whenever you, again, have a sample and unknown that is in a matrix that you cannot easily replicate in the lab. Another very common technique is what's called an internal standard. An internal standard is something that you are going to add that is similar but distinct from the analyte that you want to analyze. So in standard addition, you have to add the exact same analyte that you are interested in. In internal standard, you have to add something that is chemically distinct, so that you can somehow distinguish it, but yet you want it to be as similar as possible to the analyte that you're interested in. The internal standard is added to help account for all the issues that probably happen, not to pick on organic lab, but probably happen in organic lab. The internal standard is added as early as possible into the process, and you add a known amount of the internal standard. So in this case, this is our internal standard. And it can somehow be distinguished from the species that we're interested in. So you add it as early as possible. And then at the end, you calculate how much internal standard is left. Because you're always, whenever you're doing anything, any physical manipulation, you're going to lose some. You never get 100% transfer. You never get that last drop out of the bottom of the bottle. If you're using a syringe to suck up solution, there's always going to be a little bit of sample still left on the inside barrel of the syringe. If you're doing a column chromatography, there's always going to be a little bit of stuff left in the column. You never get 100% out. So anytime you do any kind of physical manipulation, no matter what it is, whether you're transferring from one glassware to another, whether you're doing a column chromatography, filtration, what you're doing, you always lose some. By adding this internal standard that you know how much you've added, and by making the internal standard as similar to the molecule that you're actually interested in, the assumption is made that you're going to have similar losses to the internal standard as you do to your analyte that you're interested in. If you spill half of the mixture, the assumption is that if it's well mixed, you spill half the internal standard and half of your product. There's no reason that if you're well mixed to assume that when you spilled half of it, all of it was internal standard and none of it was product. It should be equal amount to each. If there's a drop left in the bottom of the beaker when you transfer, the assumption is that you're going to have equal amounts of the internal standard and the unknown. So in the end, after you've done all of your manipulations, whatever it is, column chromatography and transfers and injections into the GC or whatever you've done, you can calculate how much unknown you have. You can calculate how much internal standard you have. Knowing how much internal standard you started with, you can say how much did you lose. If you lost 10%, the assumption is that you must have also lost 10% of your unknown, of your product, of your whatever you're interested in. So you can then adjust the concentration of that to include that 10% that you know must have been lost somewhere along the way. So internal standard is going to correct not for the presence of other things, other components, other matrix, like standard addition does. It's going to help correct for all the losses that are going to naturally take place, even if you're doing all of your procedures correctly. You're always going to lose a little bit someplace. So it's kind of an internal way to keep track of how much you've lost during the process, and then use that amount to correct for the actual concentration that your unknown really should be, because you'll have lost some of that as well. So to do that, you again have to be able to tell them apart, because you have to be able to see how much internal standard there is and how much unknown there is. So they can't be the same thing, but you can't tell them apart. They have to be different. But you want them to be as similar as possible so that they both stick to the same amount to the glass, or they both stick to the same amount to your column chromatography media or whatever it might be. They can be two distinct chemical compounds. Or, very commonly, what's used is they're the same compound. The internal standard is isotopically labeled. So it's got deuteriums on it instead of hydrogens, for example. Or it's got oxygen 18 instead of oxygen 16. In that case, chemically, they're the exact same molecule. They should react, should stick together in the exact same way, but they will have, since they have different isotopes, they'll have two different masses, and now you can use their masses to separate out and figure out which is which. But in any case, they have to be somewhat chemically distinct so that you can tell them apart. So how can these be used? So you have a sample with a known analyte and standard ratio, for example. You know the concentration of X, you know the concentration of standard. You can obtain their absorbance readings, the absorbance of X, the absorbance of the standard. You can then add a known amount of standard to an unknown amount of analyte. The two known concentrations of the standard could be the same, it makes the math a little easier, or they could be different. They don't have to be the same. What's important is you know what they each are. You then go through all of your processes, all of your cleanups and your reactions and everything else that happens. And you then measure the absorbance of the unknown and the absorbance of the standard. And we then set up a ratio. The unknown amount of analyte over its standard, over the known amount over its standard, is equal to the absorption of the unknown amount over the standard absorption over the absorption of the known over the absorption of the standard. So again, if in both steps 1 and 3 you keep the concentration of the internal standard the same, it makes the math easier because these will be the same. So they don't just have to. So for example, if we have a solution, we make up a solution of 0.15 molar ketoprofen and 0.385 molar benzene, chemically somewhat similar with an aromatic ring of ketoprofen. And they're analyzed using absorption. For the absorption for the ketoprofen is 0.478, for benzene is 0.251. And an unknown sample of ketoprofen is then brought to the lab and mixed with some internal standard benzene is at 0.265 molar. Everything is, the lab does for the sample is done, all any reactions or cleanup, chromatography, whatever. And we now measure the ketoprofen at 0.256 absorbance and the absorbance for the unknown benzene at 0.157. You should now be able to determine the ketoprofen more accurately in the unknown sample. Realizing that by the steps that we've done to that unknown and treating it, maybe dermatizing it or cleaning it up or pouring it from one container to the other, we've lost some. We have also presumably lost the same amount of our benzene. We can set up our ratios. We have the concentration of the ibuprofen unknown, ketoprofen, excuse me. over the concentration of the benzene that was added to it. That's over the ratio of the concentration of known ketopropin that we had over the concentration of the known benzene that we were using at that step. And that will be equal to, in the numerator, the absorbance of ketopropin from the unknown solution, 256, over the absorbance of the benzene of the unknown solution, 0.157, over the absorbance of the ketopropin of our known solution, 0.478, over the absorbance of the benzene in our known solution, 0.251.